This is a quick introduction to normal probability notation. Let's take a quick look at some vocabulary. We're going to use different words to describe the area under a normal curve. And the area that we describe is sometimes it's below a given x value and sometimes it's above a given x value. And sometimes the area that we're looking at is between two given x values. But the thing is that we have several different words that we use to describe the same exact thing. One of the things that we've already looked at is the idea that area under a curve is important. And the other thing we've looked at is that that area can be represented as a percent of the total area under the curve. Sometimes also you will find that the word fraction is used to describe this area. Sometimes the word proportion, and also the word probability. And the word probability is kind of the one that we really care about because a lot of times we're using a normal curve to determine the probability of the likelihood of something happening or not happening. Okay, so I want to make sure that you guys know these words are synonymous when we're talking about normal curves. Okay, so next thing is the idea of a standard normal distribution. Now, you would think a normal distribution would be enough, but no, we need a standard normal distribution. Let's take a look at the characteristics of a standard normal distribution. First, every standard normal distribution has a mean that is 0. And every standard normal distribution has a standard deviation that is 1. And in fact, this picture down here in the lower right corner is an example of a standard normal distribution. Now, one of the effects of the first two criteria is that this third thing is that all of the labels on the x-axis of a standard normal distribution are considered z-scores. So in this case, when you look at the numbers on the x-axis, the mean is 0, one standard deviation directly under the inflection point in the normal curve lost my train of thought. Let's get back to this. Anyways, these numbers down here you can see, we could call them x values, but they are also z-scores because the mean is 0 and the standard deviation is in units of 1. So 1, 2, 3. Okay, so anyways, just wanted to introduce you to that idea. When we look at a normal curve like this, we know that this negative 1.6 is going to be a z-score, not necessarily an x value. That means that we don't have to convert it to a z-score, and that's good news. Okay, so why am I telling you this? Why am I giving you this video at all? Let's take a look. What is the problem? Well, I have a saying that I've been using for most of my life, and it goes something like this. The first step in solving any problem is recognizing it exists. So let's take a look at the problem that I have recognized, and I'll share it with you. Many students, when they first encounter z-scores in percents, they mistakenly write out their answers like this. Negative 1.6 equals 0.0548. Now, if you go to a z-table and you look up the z of negative 1.6, you will definitely see 0.0548 in the middle of the table. But those two numbers are not equal. I mean, clearly negative 1.6 is not the same as 0.0548. So what would be a better way to write this out? It would be using some normal probability notation. And here's what it would look like. We would pronounce this as the probability that z is less than negative 1.6 equals 0.0548. And of course, you could also call that 5.48%. Okay, so let's take a look at some examples of using this notation so that you can see it a few times from several different perspectives. Okay, so let's say that we have a graph that looks like this, a curve that looks like this. Because the shaded area is to the right of the negative 1.6, we would say that the probability of z is greater than negative 1.6 is equal to 94.9452. Now we could get that 94.52% from a z-table, or we could use a normal probability calculator, and I have a link to one in this slideshow, so I'm going to click on it and show you what it looks like. Here we can put in values for the mean and standard deviation, and we can put in various x values, and we can make it less than or greater than. We just have to choose to enable it. Now, I'm going to make this slide available to you in addition to the video, and you will be able to click on these links and find the normal probability calculator. Okay, anyways, let's keep going with the notation. So, in this case, I have a z-score of 1.2, that's where my cut point is, but the area is shaded to the left instead of the right. So yeah, in this case, I would say the way that I would describe this is that the probability of z being less than 1.2 is equal to whatever I found in my z-table or my normal probability calculator. In this case, it's 88.49%. All right, let's take a look at another example. Now, in the real world, we don't tend to see z's don't just fly at us. In the real world, mostly we're looking at values of things like the weight of a person or the height of a person, or things like that. And so for that reason, usually we're dealing with x values. Now, here's some additional notation. When you see n with parentheses and two numbers inside, the first number usually stands for the mean, and the second number usually stands for the standard deviation. Now, in some cases, I have seen it where the second number is the standard deviation squared, also known as the variance. But in our book and in the software we're using, Math Excel for School, we're going to treat the first number as the mean, second number is standard deviation. Now, if we're told that we have data that is normally distributed with a mean of 125 and a standard deviation of 25, we can then use that and this picture to figure out how to write out the percent or the area. And again, the way that we explain this, we don't say that 85 is equal to 0.0548. And we don't find the z-score of 85 and then say that z-score is equal to 0.0548. What we do is this. We say the probability that x is less than 85, because that's what's depicted in that is the problem that we've been given. The probability that x is less than 85 is equal to 5.48%. And again, we can get this value by using a normal probability calculator. And with a good normal probability calculator, you can either put in a z value or an x value, as long as you put in the appropriate mean and standard deviation. Remember, for a standard normal curve, mean is 0, standard deviation is 1. For the normal curve we're looking at right now, the mean is 125 and the standard deviation is 25. So we'd have to change these in order to use this calculator. And then we would go and say x is less than 85. So I would change that around, check this box, put in the x of 85. And one last thing with this particular calculator, I would press the scale to fit button. And voila, I get the probability, and then I can go ahead and use that to answer my problem. Neat, huh? Okay, let's keep going. So this is just a similar example, except the shading is above the x value of interest. Again, the mean is 32, standard deviation is 3. We want to know the probability that x is greater than 34, so that's how we write it out. And by the way, I'm going to expect you to use this notation now that I've shown it to you. So when you write out your work by hand, you need to put probability of either x is greater than something, or z is greater than something, or x is less than something, or z is less than something. Anyways, if we go to look it up, probability of x is greater than 34, given this mean and this standard deviation, is about 25.25%. Now, the next thing that I have for you has a fancy name, continuous distributions. And I have to tell you this. What I'm about to tell you is going to sound like magic to some of you. It is kind of like magic, but it's like real magic. And by the way, the author Arthur C. Clarke once said that any technology that is sufficiently advanced is indistinguishable from magic. And that's the way math is sometimes. It's just indistinguishable from magic. So let's take a look and see what I got. Okay, so when you have something known as a continuous distribution, and that's what normal curves are, they're continuous, okay? And to be more clear, it means you have an infinite number of possible x values, okay? And our normal distributions do have an infinite number. I know that sometimes we see, like 125 and 150 and 175, but there could be an infinite number of values in between those, okay? And there's nothing to say you couldn't have 125.00000000001, okay, and even further down the line than that. So we consider a normal curve to be a continuous distribution. Well, if you have an infinite number of values and you squeeze them into a finite amount of space, then each one of those values is going to be very small. And it turns out, as a result, the probability that z equals 2.3 or that x equals 847 is 0. The probability that z equals one exact number, even if it's a nice round number, the probability is 0. I told you I was going to introduce you to some magic. Now, I know some of you are in disbelief, but that's okay. You got to hold off on that for a minute. Now, there is a consequence to this, and I need to share this with you, okay? The consequence is this, is that if you have a problem statement that indicates that x or z is greater than or equal to some number, it means that all you have to do when you go to look up the probability is look up the probability that z is greater than that number or x is greater than that number. You don't have to do greater than or equal to. The or equal to has a probability of 0, and when you add a probability of 0 to any other probability, you get that probability. So in this case, if we have probability that z is greater than or equal to negative 1.4, that's the same as the probability that z is greater than negative 1.4. You don't need to include the or equal to. Likewise, if you're looking at the probability that an x value could be less than or equal to some number, it's exactly the same probability that x could be less than that number. You can just throw away the or equal to. Just wanted to share this with you in case you ever run across this in this class or in a future statistics class. It'd be kind of nice if you knew the magic. All right, so one final example along these lines, just to be perfectly clear, is that if you did the calculation, if you had a normal distribution with a mean at 32, a standard deviation at 3, and you wanted to know the probability that x is greater than or equal to 34, you would calculate you could use the normal probability calculator. You throw in the mean of 32, standard deviation of 3, you throw in the x. By the way, you'll notice in the normal probability calculator, there is no or equal to because it's unnecessary. Anyways, if you went to go and calculate greater than 34, the percent that you get would be the same as greater than or equal to 34. All right, people. That was a little bit of a marathon. You did well. You hung with me. Good job.